Okay, I'll go ahead and get started here. Welcome everybody to the third of our four-part series of Southern New England Vegetable Growers Meeting. This is every other Thursday from 3:30 to 5. Those of who you don't know me, I am Shuresh Ghimire, Assistant Extension Educator at UConn Extension. Before we begin, I'd like to give a big thanks to Sue and Genevieve at UMass Extension and Andy Radin at URI Extension for doing the heavy lifting to put together this webinar series. Thank you so much. This is exciting that we have 370 people registered and 159 or 160 people on board. That is awesome. And this is a webinar format as in the past webinars. So if you have questions at any time, please enter them in the chat box. We'll have time for question and discussion at the end as well, where you can raise your hand and we will get you unmuted and you can speak up and ask your question. For today's webinar, there is no pesticide credits, so you don't have to provide your pesticide information. And we will be recording this session and will be posted at the UMass YouTube channel, and you will receive a link to the recording when it is ready. That's basically the format of the webinar today. We have two great presenters today, Rosa Raudales and Andy Radin. Dr. Rosa Raudales is an assistant professor and greenhouse specialist at UConn. Her main area of interest include water management and hydroponic food production. Our next presenter, Andy Radin, is Agriculture Extension Agent at University of Rhode Island. Andy has been working, investigating the different types of potting mixes, and we'll talk about it today. So we will start with Rosa. Rosa, please take it away.
Okay. All right. Can you hear me and can you see my screen?
Yes, yes.
Oh, all right. Thank you, Shuresh. Thanks everyone for being here. So today I'm going to cover three topics. I'm going to spend most of the time talking about nutrient programs, and then I'm going to fly through the last two subjects. But hopefully by the end of the presentation, you're going to get a good sense of how to make decisions. One thing that you should know, every time I give a talk, I'm not going to give you a recipe, because one of the things that you will learn from this presentation is that what your neighbor does might not necessarily apply to what you should be doing. So before I get into the subject, I would just like to thank some of the sponsors of my program. They sponsored the different activities in terms of research and outreach that I do. And I would also like to encourage you to visit eGrow. It's egrow.org. It's a website where we develop a lot of education material for growers, specifically for greenhouses, and we do both information for ornamentals and edible crops. So I encourage you to register. It's free, and we send new information every week. So go for it. So we're going to start with nutrient programs. And one of the things, if you're a field grower, one of the things that you want to change your paradigm when you think about growing your seedlings in the greenhouse is that every time you grow in a container, and every time you're thinking, okay, I'm going to deliver the fertilizers by using soluble salts, whether you're putting them in the mix or whether you're applying them through the irrigation system, what you're thinking about what you're applying is really you're delivering this nutrient solution. And what the plant receives, it's not just the fertilizers you're applying here. Let me put my pointer on. Not just the fertilizers that you're adding, but you're also adding whatever comes in the water. And unless you're having a really pure source of water, by the end of the presentation, one of the things that I want you to take from here is that you might be growing the same seed, using the same media, and growing at the same time of the year in the same state, but you might not be, and using the same fertilizer, and you will not get the same results from your neighbor growers. Because if the water quality is really different from your grower neighbor, then your results are going to be different. So that's the one thing I hope that you will take from this section of the presentation. So just a general reminder that when we develop a nutrient program, one of the things we want to do is, first of all, we want to make sure we provide all the elements plant needs for growth. We want to provide not just all of them, but we want to make sure that we provide the right amount that the plant needs. In seedlings, the right amount tends to be relatively small compared to like grown crops or fruiting crops or fruiting stages. And then the final thing is that, especially, and this is true and regardless of the system you're doing, hydroponics, soil, or just growing in media, you want to enhance the nutrient availability, because you might have the right amount, but if the plant cannot use it, then it's basically like there is not the right amount in there. So when we talk about nutrient availability, we're always going to talk about making sure that we have the right pH for the crop to grow. And again, like I said just a few seconds ago, one size does not fit it all. You can think that those different animals that are looking at that store window are your different water sources, and you're trying to make it fit in your production system. So we're going to go step by step on how we develop a nutrient program. So you're going to start with a water quality analysis. And by this, I mean, the first thing is when you collect your water sample and you send it to a lab, the first decision you want to make is you want to make sure that you select the right lab. Some labs will do water testing for drinking water, but the results that they give you are not things that you are going to use. You might use some of them, but they don't give you complete information. So the first thing you want to think is, I need to send my water sample to a horticulture lab, because they will give you a breakdown of the different ions that are essential for plant growth, or they will give you information such as pH, electrical conductivity. For example, it's something you don't see on drinking water. And we're going to break these elements in a few seconds here. And then it gives you all the other elements that the plant either use or they can affect plant growth. So that's the one of the things you want to do, right? Once you get your result, you're going to check for several things. You're going to check for total salts. We'll talk about that shortly. You want to check for specific salts, and that is one of the big differences from getting a drinking water test and getting a horticultural water testing. So as a good example, one of the common problems we find is some water sources have a lot of calcium, right? So if your water has 200 parts per million of calcium to begin with, that will affect the type of fertilizers you're going to apply, because you're not going to add more calcium in your fertilization. So when you get your water test, you want to go line by line and see what are the things that are in my water already, and what are the things that I should not be providing more in my fertilizer. The other two things you're going to look at is the alkalinity. One of the things, we're going to talk in detail about what that means, but one of the things that I want you to take from just here is that when we talk about alkalinity, one of the confusions is that again, if you either do like field testing water or drinking water, you're going to look at a number called hardness, and hardness is presented in calcium carbonate equivalents, very similar to alkalinity, but the values are different. The interpretation of how you use those two are very different. So alkalinity, it's different than hardness, even though the labs present them in the same units. And then we're going to talk about pH. So again, get that full test. Make sure you get one at least once a year before your season starts, and make decisions based on that starting point. So looking into that water test, the first thing we look at in any test is that we look at the total amount of salt. And the indicator that we use for this is called electrical conductivity. And this is really just a measurement of the ability of the water to move charges in the solution. But our interpretation for how we use it is the total concentrations of salt in the solution. Many of you, if you're working in the field, you're probably used to the term total dissolved salts. It's the same type of measurement. The difference is that total dissolved salts is an indirect measurement from electrical conductivity. The reason I would encourage you to use electrical conductivity is because when you try to match what you have in your water, what your fertilizers have, and what the published recommendations are giving you, they're usually using this unit as a measurement. So try to switch from the total dissolved solids and try to start using electrical conductivity. The interpretation of electrical conductivity is that it just tells you if there's a lot of salts or there's a low amount of salts. Typically, when you find natural water sources, these are the different elements that you will find that contribute to electrical conductivity. There are other factors such as fertilizers that will also contribute to electrical conductivity. And the electrical conductivity doesn't tell you which ions are in there. And that's why you need to get your full test to make sure that you understand what's in there. As a general rule of thumb, one of the things that we tell our growers is that if you have a pH and EC meter in your operation, you can constantly monitor the EC of your water. And then if you notice that the EC goes above 0.5, you tend to send that for a full analysis. If it's under 0.5, you can assume that most elements are really low and they shouldn't affect your fertilization system. Now we're gonna talk about alkalinity, and I think this is kind of at the center of what you wanna understand from this section of the presentation. So alkalinity, like I said, it's different than hardness, and it's also different than alkaline. So an alkaline pH means a pH that's high, right? But water alkalinity refers to the neutralizing capacity of a solution. An easy way for us to remember what alkalinity means is imagine you have your water, and your water has something that reacts like dissolved limestone, right? And what contributes to that dissolved limestone, which is not actual limestone, but it reacts in that way, are bicarbonates and carbonates, right? So if you have a lot of that, imagine that every time you're irrigating, and picture yourself, right? I'm irrigating my crop with a hose. If you have high alkalinity, every time you're irrigating, the pH of your substrate is going to go up, right? Because every time you're liming the substrate, basically. If the alkalinity is really low, it means there's very little in your water to react to anything that would cause a pH to drop. So an extremely low alkalinity is not good. An extremely high, it's also not good. One is easier to manage than the other, but we'll look at that as well. So just to look at what I just described and try to visualize it, what we have here is, imagine you have a water sample. They both start at the same pH. And I'm trying to estimate how much acid I need to lower the pH of that water sample, right? So what you're seeing here is the amount of acid that you're adding, and see how that reacts in the pH to drop. The red line has high alkalinity. Again, like high dissolved limestone kind of reaction. So I'm adding acid, and you can see that the reaction goes slow. You need to keep adding acid in order to neutralize all the alkalinity and reach a pH of 4.5. If you have no alkalinity, you add a little bit of acid and the pH drops very quickly, right? So that is the effect that alkalinity can have in your water. And that's also the effect that accumulates usually on the substrate in the media, right? So again, we're talking right now about what's going in the water. And now we're gonna move into understanding how these affect what's going on in the substrates. Before we move into the substrates, one of the things that I wanna show you is that if your alkalinity is extremely high, the way to manage it is you just acidify, right? If you go to this website that I mentioned earlier, ecro.org, you need your water test, and you're gonna enter your information saying what your alkalinity is, what your target is, what acid you wanna use, and then this calculator is gonna give you the information, and it's gonna make the calculation of how much acid you need to neutralize that alkalinity. But you need the test to make sure that you have the right inputs, okay? Now we're gonna switch to pH, and in a moment, I'm gonna come back to putting pH and alkalinity together. So as you know, pH affects the nutrient solubility in water and substrates. So it's important that when we're talking about pH here, we we keep an eye on my words when I talk about water and when I talk about substrates, because there's a slight difference here. So so the pH, whether it's in the water or the substrate, it will affect the nutrient solubility, right? And by solubility, you've probably seen this graph many times, and you know that, for example, in micronutrients, when the pH goes up, the iron precipitates and becomes insoluble. The plants cannot use it. For example, in the greenhouse industry, when the iron is really low, some crops are really sensitive to iron toxicity, and you tend to see toxicity because when the pH is low, the iron becomes more soluble. So the total concentration is there, but it's the form that changes in how the plant can use it, right? So this happens both in water and substrates. So when we think why water pH matters in terms of fertilization practices, it's because if the pH of your water is in any of the extremes, too high or too low, you're going to end up with problems of solubility, either too much or too little. Low pH also has the problem that it might directly have effects on the roots, but you also, most of the time, you want to think about the solubility. If you're injecting something in a solution and things are precipitated, you cannot distribute the fertilizer very well. So if you have an extreme in terms of pH, of water pH, and by that I mean something above 7, 7.5, or something under 5.5, then you need to adjust the water pH just because you're trying to address the solubility of the fertilizer that you're applying in the irrigation system, right? But when it comes to thinking about the pH of the substrate, so going back to our target is to have in those little cell plugs that we're growing those seedlings, the right pH. The pH of the water has very little effect on the pH of the substrate, okay? And I'm gonna show you how this works right now. As an example, if you have, and this is something that we measured a few years back, if you have a 1 liter of a container and you irrigate that container with 1 liter of water per week for 15 weeks, and the quality of your water is you have a pH of 9, and then you have an alkalinity of 200 parts per million calcium carbonate. When you convert that pH 9 and that alkalinity, and you convert it to something that's called milliequivalents, which is basically trying to convert them to units that are apples to apples, what you see is that the pH contributes very little to the base as a base, and that the alkalinity is contributing a lot. The equivalent of 200 parts per million is the equivalent of 5 pounds per cubic yard of limestone. So you can see that this pH has very little effect on the pH of the substrate, right? Going back to what I said earlier, this pH would affect the solubility of the fertilizers in the solution. So you need to address that pH because of the fertilizers you're diluting in the water. But managing the pH alone will not be the factor that will affect the pH of your substrate. So this is just another example to emphasize the same point. If you have 2 growers here, grower A has a water that has a pH of 9.3, and then grower in an alkalinity of 71. Grower B has a pH of 8.3 and alkalinity of 310. So which grower needs more acids to lower the pH to reach, for example, 5.8 was this example? You can see that the amount of acid that the grower B needs is way higher, even though the pH is lower. And this is something that you could try to do yourself. You could go to that alkalinity calculator, and you're gonna see that the alkalinity is always gonna be the strongest factor in determining the pH of the substrate, right? So this is just the same example from Bailey and Bilderman, who provided this example where they actually calculated how much of that acid was needed, and they can see that grower B needed 4 more times more acid to reach the same pH. Okay, so I hope I have convinced you up to now that alkalinity is going to affect the pH of your substrates, right? And again, the easiest way to remember that is think of, I'm irrigating, every time I'm irrigating, is there a lot of limestone that I am adding with every irrigation? So once we understand this, we can make selection on the fertilizers that are gonna match that water quality. So the simplicity of this can be that if you just think, okay, my water has high alkalinity, I just need a fertilizer that has an acid reaction. Which one is that? We're going to show you shortly. If the alkalinity is extremely high, you always want to acidify first and then use a fertilizer that is a little bit milder, because using a fertilizer that's strongly acidic is not a sustainable practice, and I'll show you a little bit why. Water with low alkalinity, you're going to use a fertilizer that has a neutral reaction. Again, remember that green line. If you have a little bit of acidity, that's going to contribute to extreme drops in the pH. And then you're going to go by just looking at the other elements and see where they are, and then adjust your fertilization based on that. As an example, calcium or magnesium tend to be high, especially calcium. So if that's the case, you would just select a fertilizer that's low in calcium or magnesium. So the fertilizers can have an acid or a basic reaction depending on the nitrogen form that you find that it's abundant. So ammonium and urea are both acidic fertilizers. Some fertilizers are just contain ammonium and urea. Nitrate is a weakly basic fertilizer, so it tends to be a very neutral fertilizer. Nitrate is a preferred form in seedling production, because one of the things that you don't want when you have a small cell is to have a lot of fluctuation. So nitrate is desirable because it would keep things really stable. Unless you have those extremes in your water, then nitrate tends to be the preferred form. Ammonium, we can use fertilizers that contain a little bit of ammonium if we have an alkalinity that's compatible with this. But one of the things that you want to keep in mind is that you can't have like pure ammonium, or you can't have too much ammonium, because it can be toxic. And the other thing is that we typically want to have compact and like and good growth. You don't want to have soft growth. So ammonium tends to like stretch plants a lot, and probably that's not a good characteristic for seedlings. So just to go back to how the fertilizers would look, depending on the concentration of ammonium and urea, which are the acid forms of nitrogen. And just I want to say one thing going back to this. If you mix these fertilizers and you put a pH meter, that's not how it works. This is a reaction. So once these fertilizers react in the media and with the plant, that's when the acidic or basic reaction would happen, right? So most fertilizer labels are going to give you some sort of indication of where they lie in terms of their compatibility or reaction. Some of them give you some labels that say with type of water 2 or type of water 3, and then they tell you what that water type means. But you can make sure that you double check that by yourself. And you should know that anything that has more than 20% ammonium and urea together as a total form of nitrogen is going to be an acidic fertilizer. You would never want to use something like 2177, which is extremely acidic. We use those fertilizers for like point treatments when we want to like lower the pH really, really quickly, but we don't want to use them constantly because of what we've talked earlier about ammonium phytotoxicity. So we selected a fertilizer, and now we want to select the right amount of fertilizer. One of the things that I highly recommend is that you rely a lot on your seed company. This is an example from Ball Seed, and it's not that I'm endorsing any company, but they do have a very nice, they do have in general very nice production guides. So when you look at this and we're trying to grow plugs, we get the different seeds, and there are different stages that we're used to communicate about where our seedlings are. So stage 1 is when the radicle just emerges, and you can see that at this stage, they don't recommend any fertilizer. Stage 2, it's when the radical emerges and you start to see the cotyledons, right? And stage 3, it's when the cotyledons expand and you start to see some true leaves. And stage 4 is when you have the true leaves as a primary vegetative stage. And you can see that at stage 3, these are the different crops. Each row is a different crop. They provide a recommendation on how much fertilizer you should apply. And they also provide a recommendation on what the electrical conductivity should be. So you can have within a range you have some room there. And then you have also a recommendation on how much fertilizer you should be applying for that stage. For plugs, you tend to like stay on the lower end of fertilization all the time, lower frequency and lower concentrations. But you can see that for this example here, for broccoli or Brussels sprouts, they went from once a week to 2 times a week to just kind of increase the rate of fertilization they were applying. So again, rely a lot on your seed companies because they do a lot of studies on the different species they have. The other thing is if you don't want to rely on your seed company, you can like use them as a reference more or less because they also are a good reference in range. You might not be growing the same broccoli that they're saying, but I'm sure that if you follow relatively close their crop production, you will get a good quality of broccoli. And then, so you have the 100 parts per million. So how much does that translate into how much you're actually mixing there? You, again, go and rely on your fertilizer label. This is just an example that I pull it from the website. And basically, they'll tell you if you have 100 parts per million of nitrogen that you need to apply. If you're using an injector, it tells you how much to mix. In this case, it tells you that the units are ounces per 1 gallon. If you don't have an injector, it tells you how much the conversion would be and how that would translate in terms of parts per million. So the labels do tell you a lot of information that you can use to estimate what's the right amount. When you went from the catalog to tell you 100 parts per million, and then you go to your fertilizer label to make sure that you have the right amount that needs to go in there. So now we are ready for fertilizing. And the next step would be to monitor the pH and electrical conductivity. The ways that we collect samples from plugs is that we can either squeeze the plugs. Not a lot of people like to do that. The benefit is that it's a non-destructive sampling. The disadvantage is that you're going to squeeze your plugs a little bit, right? And basically you measure the pH and electrical conductivity directly in the solution. The other alternative is a destructive sampling where you get a few random plugs and then you just collect all the media and put it in a container and you either saturate the media or do that 2-in-1. And then you measure the pH and EC directly in there. So once you've been tracking for a little bit, with seedlings, they go so quickly that you might not need to be doing this on a continuous basis, but you would usually do it if you see damage in the crop or you start seeing that the color is not where it should be. And in general, you want to follow the original crop guide, but just in general, you can say that if the EC is low, you know that you need to add more fertilizers. Just because the EC is low, you should not add the fertilizers. You want to see if you match that with the symptoms of the plant. If it's in a really low place, but the plants look well, you can increase the fertilizer by a little bit without having to overdo it. If it's high, you start by reducing the amount of fertilization, and then you start with leaching with clear water to make sure that you get rid of some of the abundance of salt. If the pH is low, then you're going to make sure that you're only using fertilizers with a neutral reaction. That means fertilizers that only have nitrate as a nitrogen form. And a lot of the fertilizers that we use for plug production, like 13-213, has only nitrate. In an extreme scenario, you would inject liquid limestone. You can inject that through the irrigation and it's safe for seedlings. And then if it's extremely high, you can use a little bit more ammonium and then make sure if you're in an extreme situation, then you can acidify slowly. You acidify once, keep tracking, and then repeat if needed. So that's what I have in terms of fertilization. Now I'm going to switch to chlorination. So chlorination is one that before we get into the subject, I want to make sure we have our concepts clear. So chlorine, the one I'm going to talk about today is what we commonly known as bleach, but it's basically a disinfectant, right? And it can be used in surfaces, it can be used in water. Today we're going to talk about how we use it in water. Chlorine is also an element with the symbol Cl. It's very rare to find it in nature, but it's also called chlorine. And then chloride, you might have seen these listed on the water test at the beginning, chloride is an ion. Chloride is something you might find in water. It's something that it's very similar to fluoride, but chloride. So just make sure that we don't confuse those, because when you get your water test, you're gonna get chloride concentrations. If you wanna measure chlorine, that is a different test. So just make sure that we know the difference for those. So we're gonna talk about chlorination. So chlorine can be obtained in different forms, or not so much obtained, but delivered in different forms. You might hear in the industry that there are different, that there are advantages of using one versus the other. I think the advantages are more in terms of the practicality of what fits best within your production system. At the end of the day, the mechanism that the different forms of chlorine work is the same. And the way chlorine works is it works through something that's called oxidation. It steals electrons, and then it also adds chloride ions to the cells. But at the end of the day, when we look at the active ingredients, it's this hypochlorous acid that we're looking at here, and these hypochlorite ions that are going to react with whatever we're trying to target. And it doesn't matter if you started with a gas or with a solid or with a salt, you're gonna get the same product at the end. So the efficacy of the different types of chlorine should not be measured. The other thing is that, again, we have those different forms of sanitizers. I'll touch on this shortly, but you also have, so these two are what's known as free chlorine. We also have something that's kind of combined form of chlorine. And this one usually forms when the hypochlorous acid interacts with ammonium or ammonia, and then it forms something called monochloramine. Monochloramines are also sanitizers, so they would also kill organisms if that's what you're trying to target. The difference is that it reacts a little bit slower, and it's actually one that's used a lot in factories where they have like really long pipes. Because of their slow reaction, you can disperse it and make sure that it reaches far places. And then we're going to talk a little bit about that pH shortly. So pH is essential to make sure that you have effective chlorination applications, because what we have here is the total amount of chlorine and then the abundance of the different forms. And what you can see is that when the pH is 7.5 or less, hypochlorous acid is the most abundant form, right? If the pH is higher, hypochlorite ion is the most abundant form. Hypochlorous acid is the strongest form of the sanitizer. So if you want it to be really effective, you have to go there. And I forgot to add a graph, but there's been graphs about using the same concentration of chlorine and its effect on mortality on plant pathogens. And definitely, if you have the same concentration, but you just change the pH, the mortality is very different. Basically, you have higher mortality at lower pH. The other thing that affects the efficacy of chlorine is what's in the water that will generate sanitizer demand. And this sanitizer demand is, if you think about you're injecting 5 parts per million of chlorine, and whatever's in the water, and that can be organic matter, it can be inorganic particles, whatever dirt is in the water, the chlorine is going to react with that. And if there's a lot of dirt, you will have very little residues that will travel through the irrigation. If you're using chlorine in your irrigation, one of your goals is that you have some left to travel through a whole irrigation, right? To kill any pathogens that you're trying to target. But if the water is very dirty to begin with, you're not going to have the effect of having that residue of chlorine. So think about what is the way to do this. First of all, you need to filter your water because you want to reduce the chemical cost. You don't want to inject a chemical so it reacts with the dirt that you're not trying to kill. And the other thing is that you want to increase the efficacy of killing whatever you're trying to kill that's going to affect your crop. So this is just another way to present that same concept. What they did here is they applied 2 parts per million of chlorine, and they applied different concentrations of peat, and the peat was just used as an example of a contaminant, and then they measure how much chlorine was left after 2 minutes. And what you can see is that the more amount of peat, the lower the amount of chlorine that was left. So again, cleaner water will result in a more effective sanitation. And when you think about how much suspended solids or how much dirt is usually in your water, it varies from year to year. This is the same grower. We collected samples from them. And you can see 1 year, the suspended solids in their ponds were low. The 2 years later, it was more than 3 times higher. When we look at the removal based on their filtration systems, we saw that the filtration systems work really well. And this is a common thing that you'll see, that the dirtier the water, the more it removes. So it's in other words, it's very hard to clean water that's already kind of clean. But when your water is really dirty, any type of filtration will do a lot, right? Getting rid of this last piece is always hard, but getting rid of the bulk, it's relatively easy with an easy filtration system. So now we're going to talk a little bit about dosing. And one of the things you want to think of is that when we're talking about injecting chlorine in the irrigation system, one of the things that we can't think about is that we're going to kill everything, because what you're seeing here are the different doses where we collected published information about mortality. You can see, for example, Phytophthora, the mortality goes from like 0.5 to over 2.5. So the range is really broad to begin with for just a single plant pathogen. And then when you see the different organisms, it's impossible that we're going to kill them all, right? The main reason is because we have a threshold that we can cross, and that is the threshold at which we see phytotoxicity. So for most crops, maybe there's a few crops that tolerate a little bit more, but for the majority of crops, and especially seedlings, you can't apply more than 2.5 parts per million of chlorine. Anything above that will result in phytotoxicity. And this is a threshold that we've seen that it's consistent when you apply it at a consistent irrigation application. So again, the goal is to reduce whatever amount of pathogens might be there, not to sterilize, but just to reduce the amount of microbial inoculum. And one of the secrets to make this work is that you want to reduce the concentration that you're applying by extending your contact time. One of the things that you want to think about, if you have a water source that might be a problem, you want to think about how can I extend my contact time? Because it's always better. You can apply 2.5 parts per million and let that react with your water for 5 minutes versus 10 minutes. The mortality will always be more if you let it react for the 10 minutes. So how can we do that? That's usually by trying to see if you can have storage tanks. So this diagram is just to emphasize what I said earlier. You want to have some filtration before chlorination. Then you want to inject. If you want to extend your contact time, you want to have a chemical, you want to have a tank that will help you prolong your contact time. And usually before any type of irrigation, you always have a filtration system, and then you can irrigate. The other thing with an irrigation system like this is that you want to make sure you monitor every stage. You want to make sure your filtration system, you monitor and the fact that it's working. You want to see that what's coming up here, it's cleaner than here. And then the other thing is that when you're talking about chlorine, you want to think about applying enough, but you also want to think about not applying too much. And there are different kits you can use to measure chlorine directly in the water, or you can use something like an oxidation reduction potential meter. It's very similar to a pH meter. You want to make sure that you get used to the numbers you're seeing, because sometimes changes just in the amount of dirt in the water will change this reading. But as long as you're monitoring, you can get a good sense of what's going on. And now I have 5 minutes to finish talking about selecting plug trays. Selecting plug trays is an interesting subject because when you look at a catalog for selecting plug trays, you have different sizes, materials, shapes, colors, a lot of things that you need to think about before choosing a plug tray. So there are different materials you can use in the vegetable industry. Definitely using polystyrene foam is common, especially like in tomatoes production. The benefits of this is that it's reusable, it's light in weight, people can wash it. The big disadvantage is that it can form cracks very quickly. You'll form cracks because it's a very porous type of material. And in those cracks, you have the risk of either having organic matter and debris that may carry pathogens. You also have the risk of having salts. And because we have such a small cell, and a little bit of salt can accumulate into being too much for that little plug. There are some plastic inserts you can use to avoid the negative effects of polystyrene, but then you might as well go with plastic. Plastic trays are really a great option. They're broad in range of sizes and shape. Of course, the big disadvantage of plastic trays is the environmental footprint. We need a better option. And I think you might be asking yourself, should I be using those like cow pots? I think they're fine if you're trying to sell for a consumer. If you're trying to produce like high quality plugs for your own operation, the root system doesn't develop as good as growing them in plastic trays. So I'm not going to talk about those. I'm going to focus mostly on plastic trays and selecting other aspects. So trays, you can have open versus flat. One of the things I would say, avoid the open flats, because even though it's easy to seed on them, the negative aspects of them are important enough that we should not be using them. One of them is the growth is really irregular and slow. The roots tangle so much that when you're trying to transplant, you are just damaging all the roots. One of the things that I heard on a presentation not that long ago is that when you're growing plugs, you're really growing roots. You're not so much growing foliage, right? You want to have a strong root system, and you can't get that from those trays. So we want to make sure that we use a good plug tray. One of the disadvantages of using plug trays is that it's very difficult to grow in a very small cell. One of the disadvantages is that water maintenance is really hard. You want to make sure that you have enough oxygen, that you don't overwater, and those dry very quickly. So you have to stay on top of watering. So we're going to talk a little bit more about those. The other aspect that's interesting is about color. White color trays reflect the heat. So they are good if you have conditions where you might have heat stress. Black trays, when you put them side by side with the white ones, you'll see that they'll absorb heat. So we use black trays in the winter a lot. If you're producing any of these vegetables during July, August, for whatever reason, or growing fall vegetables, you might want to think about using white trays instead of black trays, because that will limit the heat stress. And of course, consider location. I don't think we have Florida growers here, but if you were a Florida grower, there's no reason you should be growing in black trays, right? And this is just an image I got from Sakata, so I hope they don't sue me because I grabbed their images from here, but I thought it was a nice example. You can see that the white plug here, you see more branching in the roots. What they said is that when they weighed both black and plants that were grown in black and white trays, you can see that the roots, they weigh the same, but definitely the structure of the roots was very different. This one was like longer. And then when they see those same plants over time, again, this is the one that was grown in white trays. So because it had not as much stress, you can see that these are pansies, they're not vegetables. But you can see that definitely the structure of the root and the biomass, and then the top of the plant looks way better with grown with white trays. Finally, we're going to talk about selecting size and shape of the plug tray. The thing you want to think about is the deeper cells, bigger cells drain better. They're easy because they do not dry as quickly, but it will take longer to fill that cell. Because one of the tests of a good plug is the pullability. So you can pull the plug and the whole substrate and the root comes with it. So it's going to be harder in that sense. And then square cells are better than round cells. And then the other consideration in terms of the size is going to be your bench space. So I'm just going to end here and say that when the final decision to select a plug tray is that you want to match the crop to the tray to the crop in the market needs. There are crops such as arugula or any leafy crops that you can typically grow a little bit more crowded, but you can think about growing crops like cantaloupes, melons, squash, any type of cucurbits. Even when they just form their cotyledons, you know that they are pretty big leaves. So you can't crowd them too early because then you end up with stretchy plants. Crops like tomatoes, eggplants, and peppers, they tend to be a little bit more flexible on the terms of the size. I would say that's going to depend more on the market, but they are a little bit more flexible in terms of which type of plug tray you can use, and they'll grow fine even in very tight situations. So I'm going to stop here, and I think it's Andy's turn to catch up, and I'll answer some questions at the end.
Yeah, thanks, Rosa, for presenting such a great amount of information in such a short time. That's awesome. So while we transition to Andy's screen, maybe you can answer one question. There is a question about what type of acids people could add into water to neutralize water. And Sue responded citric acid and sulfuric acid. Are there other common examples?
Yeah, you can use phosphoric acid as well. I think all of them work fine. I think it's more a safety issue which ones you tend to use. So something like citric acid is pretty mild. It's also registered for organic production. So if you're on that side, you can do that. But the other ones you can use, the only consideration is whether that you're going to be adding some other elements to the crop. So you would just need to adjust, like phosphoric acid, for example. In our industry, we don't use a lot of phosphorus, so it's not used that much, but you can use sulfuric acid as well. So
thanks. Andy.
Yes. Okay. Good afternoon. So there was a couple of topics there that Rosa touched on that will kind of fit in a little bit at some point in here with what I'm going to talk about. So this is about the fact that in the market and out there on farms, there's more and more compost-based container media being used. And by the way, I tend to say media a lot more, whereas I heard Rosa say substrate a lot more. It's all the same: substrate, media, potting mix, potting soil. We're talking about the same stuff. So I visit farms mostly, and I mostly work with vegetable farms. And so I have seen on some farms, certainly not all, some very weak vegetable transplants. And in examining the media that I've seen being used and, questioning the growers, I found out, oh, you're using such and such media that has compost in it. And at times I've seen some poor results. And I want to also say I've seen some great results. So first, I'm just going to start with some basics about container media and touch on a realm that is not often talked about. First of all, just what does the container media do? Obviously, it provides a place for roots to anchor a plant so the plant can stand up and hold its leaves up to gather sunshine. And the media has to hold water that's available for plants to transpire and also to draw up nutrients in that water that it transpires. Media has to be able to freely exchange gases with the air. Carbon dioxide needs to be released because roots respire and they give off carbon dioxide. And roots need oxygen. So oxygen needs to come from the larger atmosphere and pass into the medium so that roots can use that oxygen. A medium should buffer the pH of, or should be buffered throughout the crop cycle. In other words, you don't want the pH of the medium to be dramatically changing during the crop cycle. You want it to hold fairly steady. It also, of course, supplies or holds nutrients to be available for plants to take up. And I'll throw one more point in here, and this is especially pertinent for compost-based media, is that it supports microbial activity. And in greenhouse production, in production in containers, there's a lot more interest in the microbial aspect of the plants growing in containers. Pretty hard to not buy a kind of a conventional media that doesn't have mycorrhizae in it now. How much those mycorrhizae are worth and what they're really doing is still a big question in my mind. But if a medium contains compost, you know it's got microbial activity. So this is the area that often doesn't get talked about, is the physical properties of container media. And I'll be getting back to compost in a little bit. I just want to go through some of these concepts because it has, compost can affect all of these. So these concepts are bulk density, porosity, and particle size distribution. So just to define bulk density, it's the weight of a given volume of material. So the cube on the left is 1 cubic centimeter, and it's 100% solid, and it weighs 2.66 grams. The cube in the middle and on the right, it's the same volume, 1 cubic centimeter, but especially in the middle there, you can see it's 50% solid and 50% pore space. So therefore, its density is half, 1.33 grams per cubic centimeter. This is a key issue with container media. It needs to be low density because it's contained in a pot. It's the reason why we don't use actual field soil in pots. Here I've just made a list of bulk densities of a bunch of possible media ingredients. And note, these are approximate, okay? It's actually pretty hard to accurately measure bulk density because when you fill a container of a known volume, how much do you stuff it? You can't really stuff it because once you start stuffing it, you're pushing air out of the pore spaces, and so you're compacting it. So it's kind of a tricky deal. I'll mention that again in a few minutes. So as you can see here, and you can just look at the center column, I put the grams per cubic centimeter on the right, and when we do research, we tend to use those numbers a little more. But you can see the pine bark is 24 pounds per cubic foot. Coir, which is, coconut fiber, which is getting to be used a lot more. And sorry about my pronunciation of it. I don't know. I've heard people pronounce it other ways, but when I see the word coir, it makes me think of film noir. So I'm going to call it coir. You can see compost is right up there near the top. Look at peat moss. It's half the bulk density of these materials. And you can see vermiculite and perlite are also even lower. And I've put here this kind of quote unquote ideal container media. And I put little greenhouse to nursery. So media used in greenhouses, especially in smaller cells, like Rosa was talking about, tend to be on the low end, like 9 pounds per cubic foot, whereas nursery media are denser. And especially if you think about, say, a nursery with materials in pots, they certainly have to have a certain amount of weight in them because otherwise they all blow away. And I also just put for reference at the bottom, silt loam soil. Notice how much denser silt loam soil is to all of these materials. And if you fill a pot with silt loam soil and try to grow plants in it, it might do okay for a couple of weeks, but over time, that material with repeated wetting and drying, the particles are gonna start to compact, the pore space is gonna be lost, it's gonna turn into a brick. That's why we don't use it. So here in this diagram, I actually contacted this guy who's now retired from University of California. He had a nice series of blogs with some great diagrams. I asked him if I could use his diagrams, and of course he said that's fine. So I'm gonna, I never used my, how do I get a pointer? I'm not good at this. Show presenter views, green last view. Oh, well, I guess it's too late to get a pointer, isn't it?
I think it's there under arrow options.
Oh, under arrow options. Okay, thank you.
Oh, no,
Oh.
sorry.
There's another button over there.
Not the dot, 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 but there should be like
It looks like a pen.
Oh, yeah,
a laser.
There you go, laser pointer.
laser pointer. Ooh, okay, thank you. Okay, so now this is I hope this little chart isn't too confusing. First of all, I want you to look at this hypothetical pot. Okay, this is a pot that's been watered and it's drained out. Okay, the blue, of course, is the water that's remaining in it. You'll notice there's a lot more water in the larger pore spaces at the bottom, whereas these white spaces are air spaces higher up. And so what this diagram shows is, first of all, looking across here, this solids is constant. I'm going to say if running across here is 100%, looks like about 15% here is solids. So the remainder is pore space here. That's why I put this here, pore space. And the pore spaces can be either filled with air or water. As you get higher and higher in the pot towards the top surface, there's more and more air space, okay? And down at the bottom, we have this, what we call a perched water table. I'm not gonna get too far into the how and why of that, but just the larger the pot you have, the more water that's going to be sitting down in the bottom, okay? And the taller the pot you have, the more air space you're going to have. You're going to have a taller column of air space. So, okay, here there are established criteria for the physical properties of potting mixes. Okay, so these established criteria are really loose. Total porosity, when we talk about total porosity, we're talking about all the non-solids. And those non-solids could be, again, occupied by either air or water. So greater than 50%, it's kind of not saying much, but certainly you got to have, if you're filling a container with media, you've got to have at least 50% total porosity. A lot of our mixes that we use in the greenhouse tend to be up more towards 85 or even 90% porosity. Okay, air-filled porosity, greater than 10%. And notice here I put these are mainly what we call macropores. So these are these large spaces, okay? Macropores are the large spaces, and those are the spaces from which gravity can draw water downwards. And this is just a chart showing how aeration affects plant growth. And notice here you've got somewhere around 8 or 9% air-filled porosity, where any less than that is going to be pretty bad for growing plants. And these dots are basically just like a scatter plot, increasing fresh weight of plants with increasing air-filled porosity. So here's gravity draining water out of the macropores here progressively. Here's more drainage. Okay, now this little purple arrow is actually called, it's capillary forces. Remember, water is very sticky. It sticks to itself and it also sticks to the particles in the media. That's because water is what we call a polar molecule. It has a negative end and a positive end, okay? And so now after full drainage, there's still some water in the bottom, like in the previous picture, but now there's pore spaces. And I should say that they have a term for this in the world of greenhouse growing and nursery growing. It's called container capacity. It's really the same thing as water holding capacity, or what we might call out in the field capacity. It's after gravity has drained off all the water in the macropores, and now it's only the micropores where the water is, and that's where the root hairs are going to find the water. Okay, and this, harkens back a little bit to what Rosa was talking about here. Notice now, percent solids remains constant at about 30% here. As the cell size decreases, okay, here you got a 6-inch pot. On this end, you've got a 512 tray. There's less and less air. So the macro pore space is occupied by less and less air and more water. But remember, of course, as she mentioned, these cells are very small. So when you're growing plugs, those plants use up that water very quickly, especially as they get into their 3rd and 4th week. Okay, so now we've talked about bulk density and pore space. Now I'm going to talk about particle size distributions. This is some data of my own. I've got 3 pairs here I want to show you. So first of all, left to right, we're talking about coarse particles, medium-sized particles, and fine particles in gray. Okay, and these coarse particles are particles larger than 2.38 millimeters. Medium is 0.5 millimeter to 2.38, and fine is less than 0.5 millimeter. Okay, so I was working with a producer of a compost-based potting mix, and they gave me a sample of one of their mixes that they made. I then recreated their mix, exactly the same ingredients, but I mixed it myself. I didn't use their mixing machine. And it turns out they were using a mixing machine, which is essentially it's a feed ration mixer used on dairy farms. And these are giant mixers where they mix silage with all these different minerals and stuff, and then they fill the troughs for the cows to eat out of. Well, it turns out they were heavily over-mixing, over-processing their materials. And so their version of this mix, all the same ingredients, look at the fact that they had over 50% fine particles. They had a little under 30% medium particles, and they had about 17% coarse particles. When we made the same mix, we used a different kind of mixer. We just used a drum mixer, and we had way less of the fine particles, a lot more of the medium-sized particles, more of the coarse particles as well. Now, this is a lot of coarse particles proportionally. We really don't like to see that, and that might have been because of the ingredients that they were using. Here's a different kind of a mix of theirs with different materials. And here was their version with over 30% fine materials. Our version, and also about 16% coarse. Our version of mixing, we got a different distribution of particle sizes. Having medium particle sizes at or above 50%, that's what we're looking for. We want that. So this is what we're talking about. We're talking about particle size distributions. And okay, particle size distributions really influence the pores that are in a mix. If you have lots, if you have a mix like this where it really leans much more towards fine particles, what are those fine particles going to do time after time that you keep watering? They're going to start to get settled down deeper and deeper, and they're going to start filling up all of your pore space, and your mix is going to collapse. And when it collapses, there's going to be less oxygen. You're going to create more anaerobic conditions. You might have more ammonia generated, which can be toxic to plants. So that's why we don't want lots of fine particles. I'm going to make an exception on that. When we're using germination mixes, we really don't want really coarse particles, especially if we're germinating fine seeds. So if you're raising up seeds, germinating seeds in, say, plugs or open flats or slot trays, using a fine mix is okay, first of all, because you're only going to be growing in those for 2 weeks or so, and then you're going to be potting them up to larger containers. So mainly the kind of situations I'm talking about are mixes used for growing out into full-size seedlings, ready for transplanting or for sales. So measurement of physical properties is not easy, and it's only performed by specialty labs. We did do some measuring of physical properties. This is a picture of our 1 liter seltzer bottle porometers. And these are, yes, this was the cost of 9 bottles of seltzer. And of course, when Polar Seltzer is on sale for 10 bottles for $1 a piece, you know, not too bad, right? And you get to drink the seltzer. So these are used to measure total porosity, air porosity, container capacity, and bulk density. And very quickly, the way we do this is we have to fill these, okay? Now, filling these is probably the most critical part of it because they have to be filled in a sort of, how shall I say, systematic yet arbitrary way. We aren't using some pressure gauge to press down on the tops of these when we're filling them, so we know exactly how much pressure we're exerting to stuff them full, okay? So what we do is we fill them to the top loosely till they're overflowing. Then we take the container and we tap it 3 times on the countertop so that it settles. Then we fill it over to the top. We don't tap it again. We just take a knife and we slice off the top. So we do this systematically in that way every time. Then what we do is we set these in big tubs of water. So the water level is nearly up to the top, but not over the top. Because what we want to do then is we want to saturate all the media in these containers so that it's essentially glistening on top. After we do that, with each one of these then, we lift them out and all at once suspend them over a vessel and allow all the water to drain out by gravity. And we do that by putting them on these caps here. These are like dome lids for canning jars. We set them in there and we let them drain out by gravity. So all the water that drains out by gravity is all the water that's filling the macropores. So the water that drains out, we then measure that and we know how much water was filling the macropores. Then we have to dry all the material in these. We can actually, from here, we can figure out how much air porosity. I'm not going to go into the full thing, but through this process, we can actually figure out the porosity of this material and the bulk density. Measurement of chemical properties is obviously much more commonly done. It's what people are mainly more familiar with. It's done by lots of different labs. UMaine does it, UConn does it, UMass does it, and also Penn State has a lab that really specializes in that a lot. The emphasis from labs is on the chemical attributes, and they use the saturated media extract, and this tells us pH, electrical conductivity, and available nutrients. And the extractant they use, that is the water that they use to see what nutrients are there, is deionized water. And what this tells you is the nutrients that are available right now. This is not like a field soil test, which uses a weak acid. For a field soil test, that's an attempt to estimate the nutrients which will become available over the course of the season. That's not what we do for this kind of extraction. This is just telling you what's there right now. All right, this was supposed to be about compost, right? So let me talk about compost. So there are a lot of positives about using compost as a container media ingredient. First of all, it can be made, the compost could be a locally sourced material, or it could be attained locally. That's good because we're transporting a lot of these bulk materials for our mixes very far. We're all looking to try to reduce our carbon footprints. So this could be a way to offset that. It's potentially less expensive than peat or coir, and can replace, at least in part, these materials which have their associated carbon footprint. It's a recycled resource. We like that. It has good cation exchange capacity, not as high as coir, but it's similar to peat moss. And when I talk about cation exchange capacity, I'm basically talking about the material's ability to sort of magnetically, shall we say, hold on to nutrients and maintain their availability for plants to use in the near future. Compost can counter the low pH of peat, and in fact, for reasons I don't fully understand, it actually slowly raises pH over time. And I can vouch for that because a couple of summers ago I did a pot experiment. I had 3-gallon pots of various container media growing in a high tunnel. When we started out, the pH of most of those pots was 6. And about 5 months later, when the season was over, the pH was generally between 7 and 7.2. So I thought that was very interesting. Compost can actually function as a wetting agent in mixes with peat. And that's the issue with peat. When you use peat in a mix, you do need to use a wetting agent because it's actually very hydrophobic. But once it's wet, it can stay wet. Compost is less hydrophobic and it holds its moisture really pretty well for quite a while. Compost is also a very minor source of plant nutrients. It's not a big source. It's not fertilizer, but it does have some plant nutrients. And a really interesting thing, which I don't think has been studied much at all, is that microbial activity in compost could improve nutrient cycling and also possibly suppress root disease. Negatives on using compost. Compost is highly variable, both physically and chemically. And that's because typically the so-called feedstocks, which operations which make compost, some of what they get varies seasonally. Seasonally. And so there you do get some variability in compost. There's the danger of getting poorly made or unfinished compost. It could be high in soluble salts. It could have weed seeds. It could be emitting ammonia. And it might also even contain plant pathogens. It is a weak source of plant nutrients. And so it shouldn't be thought of as a dependable, steady source of nutrients. Manure-based composts do have somewhat more nutrients in them than yard waste composts. Still, it's not a lot. Compost may add excessive amounts of fine-sized particles, and we do have to be careful with that in order to maintain porosity. It could hold moisture longer than desired. Water management is critical. I'm going to mention that a little later. It is a relatively higher bulk density material than other ingredients, as I mentioned earlier. And additional decomposition during the crop cycle could result in shrinkage, and that could lead to decreased porosity. Media formulations with compost, again, is another variable, and commercial product recipes totally vary. 30 to 50% by volume is typical. I would never recommend something with greater than 50% compost. It has excessive bulk density, low total porosity. In work I did at URI, we found that 36% compost combined with peat perlite and vermiculite made a mix with a bulk density of 0.21 grams per cubic centimeter. What does that translate to? It's probably something like 15 or 16 pounds per cubic foot. So here's another thing that's really important. Very commonly, producers of these media amend with organic nutrient sources. Things like seed meals, slaughterhouse waste products, minimally processed mineral deposits, and also mixes containing manure-based compost have a little more nitrogen. So you know, you really can't make a compost-based mix without putting in some additional sources of fertility. You really can't expect to get all that much from the compost that's in the mix. And of course, all the things I'm mentioning here are the types of things that would be allowable for certified organic production. So this is a chart here of typical nutrient ranges and pH and soluble salts. And now I'm going to say this is for conventional media. And the thing is, I think that these may not necessarily apply across the board for compost-based media. And again, I think there's a real lack of research in this area. It's really a wide open area to study. And you know, looking at pH, for instance, it says acceptable is 5 to 5.6. Here's optimal, 5.7 to 6.5. I was working with some mixes that were in the low 5s, and they produced great plants. You know, soluble salts. I saw some very high soluble salts that produced some great plants. I saw some very low soluble salts produced horrible plants. But the very high end, you know, it's hard to say. You know, this is when you're very high in soluble salts, this is where you'll start to see the effects of like fertilizer burn type issues. Again, nitrate, nitrogen, 100 to 200 parts per million. But some of our mixes had quite a bit more than that. I won't go through all of these, but I put this up here just to say, I don't know. I'm not sure if anybody knows how these relate to compost-based media. So just a little bit of work that I did at URI in this past year. We grew tomato seedlings in 6 compost-based media, including one of our own, plus an uncharged, that is unfertilized commercial peat-like mix as a negative control. We didn't use any additional liquid fertilizers, okay? We relied all the growing on whatever was built into the mixes. And all of these mixes were then sent to Penn State for chemical analysis. And I just want you to see some of these pictures here. You can see these are some horrible little scrawny seedlings that came out of their cells after about 6 weeks. These were, I think, 3-inch pots, okay? So pretty good sized pots. Whereas over here on this end, you see we have some perfectly respectable looking tomato seedlings. This is the only chart I'm going to show, but this is, I've got 6 mixes here numbered 1, 2, 3, 4, 5, and 6. Only I know what they are. I'm not going to reveal any brand names here. And along this y-axis here, these are grams in dry weight per plant. These are whole plants. We washed a lot of roots so that we could measure whole plant weights. And of course, these are dry weights, not fresh weights. And I want to show you, I'm going to show you a couple of soil tests or media tests after this, but we're going to look at this media test. This here looks like about 0.7 grams per plant. This looks like about 7 3/4 grams per plant, okay? So now we're going to look at a test from this media. And by the way, this is 4 replications here. And I'm proud to say, I'm very happy to see how tight this data is, okay? Very close, tight data. Okay, so this is the lowest producing mix. Let's look at pH. This is pretty high pH, just about 7, pH 7, okay? So what happens when we have a high pH? Means low availability of a number of nutrients. Here's soluble salts at 1.22 in the low range. That's pretty low, okay? What that's saying is that there's just not a lot of available nutrients. Look at nitrate N at 1.64 parts per million. That's nothing. The ammonium is, you know, in the normal range. Phosphorus, really high. Potassium, really high. All these other things, really high. I want special attention on sodium. really high sodium. Where does the sodium come from? Well, this particular product, which I will say is very widely distributed, is made from a lot of seafood processing waste. Okay, that's the compost that they use in it is made from seafood processing waste. And I have a feeling that that's where a lot of the sodium is coming from. And sodium is horrible. You don't want to have sodium in your container mix because it's actually going to take up space in your soil that your potassium and magnesium and calcium would like to be using in order to remain present for plants to be able to take up. Here's the highest producing mix. First of all, look at that soluble salts at 5.2. Look at the pH all the way down at 5.2 here. Nitrate, really high, okay? Everything else is in the high range here. Some of these other things are in the normal range. So, you know, it's my impression that this, first of all, I do happen to know also that cow manure compost is used in this. And there's no question that they are fortifying this pretty well with some additional organic fertilizers. So, and nitrogen being the super most obvious source. Now remember, these are organic sources, so they're not all available all at once. They will release over time. And I will tell you, over the 6-week growing period, all but one of these mixes that I tried, the plants did begin to start yellowing at successive weeks. You know, obviously the poorer mixes started yellowing earlier. The two best mixes started yellowing by the 6th week. I wouldn't say yellow, but the green started getting lighter. Okay, so things we're looking at, and I'm not saying you can just go out and take a sample and send it off and get all of these measured. I want you to understand these because I want you to think about the materials you're using. Bulk densities, we're looking for 10 to 20 pounds per cubic foot. Total porosity between 60 and 85%. Particle size distribution, we want medium particles to dominate, medium-sized particles. And that's just like in the field. Silt loams are our best soils. They give us a combination of good porosity, but also really good water holding capacity. In a way, it's the same thing in potting mixes. It's the medium-sized particles that really give us the best characteristics. pHs 5.2 to 6.0. I put this down kind of low because I don't know, in compost-based mixes, it might be okay to be down lower. And maybe Rosa might have some thoughts on that. Electrical conductivity, I wrote here especially, if for germination, you can't have ECs up this high. Okay, that'll be toxic. You need to have ECs that are probably 1 or below. And then again, watch out for excessive ammonium nitrogen, low nitrate, and excessive sodium. Also, another thing is you got to manage compost-based mixes, I think, a little more intensively. I think water management is really critical. It can become hydrophobic if it gets to dry out too much, but it does have fine particles, and so drainage could get progressively poorer over time, which is why, again, we were happy with 36% compost. Too much higher than that, and you're starting to risk more and more buildup of density over time, collapsing of the media, of the structure. So you're watering, if you could water from the bottom, that would be great. If you water to really fully saturate and then let a mix drain out and dry out, you could probably go longer periods between watering. Overhead watering notoriously does not reach down into the bottoms of cells. So I say that's just a little soapbox I like to stand on anyway. People need to water really thoroughly in the greenhouse. I've gone into greenhouses and I've seen plants doing poorly, and I've yanked plants out of cells and I show the grower the bottom and it's like powder puff. It's because they're not watering deeply enough, or somebody who's watering their greenhouses is not taking the time. Filling of containers can affect outcomes. You certainly don't want to underfill because it will reduce the soil volume for plant anchorage. But you don't want to overfill and stuff, and you don't want to stack containers up where there's going to be compression going on. Okay, so compost media can be great, okay? You need to be sure you're getting a consistent product because compost can be variable, and manufacturing could be variable. And actually, there are some of these producers who are still using payloaders to mix their ingredients. It's really hard to get consistent mixing using payloaders. Water management is tricky. Nutrient availability is not so straightforward, okay? I do recommend that nutrients be built into the mix. I have seen people watering much too much, using too much things like fish fertilizers. Fish fertilizers I've seen can actually form biofilms over the top of cells and actually make water run right off of them. I've watched it happen. You have to use so much fish fertilizer because the analysis is so low on it. Mineralization is probably enhanced by microbial activity from compost. Again, the research really is not exactly out there that I know of. A lot of factors affect the rate of fertilizer availability. I've found that manufacturers may not actually be adding appropriate amounts of amendments. So you got to watch out for that too. Water quality may interact with your compost-based mixes. Rosa talked enough about that. We know all about that now. Finally, I would like to hear about your impressions of products you've tried. You can email me and I'd love to hear about some of the various products. I'm not looking to disparage anyone. I'm just curious about what's going on out there and what people's experiences are. Okay.
Thanks, Andy, very much. Great information. By the way, are you gonna reveal the names of those products you tested at some point? Because it looks like it's a great information, but if people don't know what you tested, then the information stays with you.
Right, that's true. And I still am working on processing through all of my data, and I feel like I also might need to do some more trials, some more assays to be able to state some things more definitively. So I'm not at that point yet. But I will say there's some good products out there and there's some not good products out there.
Yeah. And so you mentioned the key parameters that growers need to check. Is that information available in the bag usually, or how do farmers know? Do they need to do their own testing?
No, farmers now, okay, so I'm going to tell you what I think that producers of these materials should be doing. They should be having them thoroughly analyzed and repeatedly, because these materials are inconsistent. Compost is inconsistent, and depending on who's doing the mixing and how they're doing the mixing, we're finding inconsistencies. So I can tell you that if you're going to buy compost, typically the producer of the compost will supply you with an analysis. I've also found that suppliers of compost aren't really giving you necessarily an analysis of the material that you are buying today. And that's a problem also. So I think that in order for producers of these materials to be doing better business, to attract more business, they should be supplying analysis to all of their customers. I mean, if somebody's going to buy 10 sling bags of a product, that's a sizable investment. And it's a big risk. And so I think they should be supplying these. I am not aware of producers supplying physical property analyses. Some, I am sure, are supplying the chemical analyses. But again, this would be not something you'd find on a bag. This would be if you're buying in bulk quantities and you're a grower.
Okay, thanks. So I'll go back to Rosa and then come back to Andy again. There are questions coming up. We crossed our time, but
Sorry.
I think it's okay. I think people will stay a little longer, a few more minutes. I had a question for Rosa. So when you do the destructive testing, where you take out plugs and put it in a beaker, and how much water do you add?
It depends if you're doing, so one of the things that I didn't mention there is whichever test you do, you want to make sure you're doing all the time, because different tests will give you slightly different results. So for example, if you do a 2-to-1, meaning 2 parts of water for 1 part of media, the numbers are slightly diluted than if you do the saturated media extract that Andy mentioned. So it depends on which method you're using. So with the saturated media extract, you just add, it's not so much about the volume, but you add slowly to reach a consistency of the media.
Okay. When a farmer sends a sample for horticulture testing, what's the tentative cost for all the results that you showed in the beginning?
For water, it's like $35 a sample.
Okay, sounds like totally worth it.
Yep.
Okay, I think those were basically the questions I noticed. For Andy, there is a question about sustainability of peat versus other materials like core. Probably little out of the scope for this presentation, but if you have an opinion.
Yeah, no, I mean, yes, it's a little out of the scope, but it also, I mean, people want to use compost and they want to use alternative products in their media for that. That's one of the big reasons. You know, peat, you hear a few different things about peat. One thing I have heard about peat, most of the peat comes from Canada. Canada's a big place. It sounds as though, from what I've read, the peat resource in Canada, while yes, it is stored carbon, it is essentially been barely scratched in relation to what is actually there. Okay. Now, as to what is actually accessible, you know, gosh, there's an awful lot of peat in northern Manitoba, but it's not accessible, whereas the peat in New Brunswick is really accessible. And so that's probably an overtaxed resource. Coir, on the other hand, comes from basically the Indian, adjoining the Indian Ocean, Southern Asia. And so this material gets shipped around the world in containers. So also, we don't know about the production practices that go into winding up with all these coconuts. You know, is there some rainforest destruction associated with production of these coconuts? And so, yes, coconut coir is a byproduct and it's getting used, but what are the ramifications on the other end? These are very difficult things to weigh. Pine bark is, you know, very commonly used now. That's really become a very large part of a lot of mixes. It's probably used a little more in heavier mixes and more nursery type mixes than in greenhouses, though it is in greenhouse mixes as well. it's, you can look online, you can see incredible photographs of these massive piles down south of where they're aging pine bark. It's quite astounding. Something doesn't look too sustainable about all that either. I don't know.
Yeah, interesting. Has Rosa or you, Andy, done any work with soil blocks?
When I was a grower, I used soil blocks for a couple of years. I was a grower for 10 years, way back when. And I tried soil blocks for a couple of years, but I actually found them to be too dense. I mean, the whole act of making a soil block is, at least looking back on it and in my growing experience later, it completely pushes all the air out of the material. So I don't like soil blocks very much.
Okay. We are, it's 5:08, so I would like to wrap up. There is one hands up. Howard asks to unmute. Is that something you can do?
Oh, hi, I just noticed.
Oh, yeah.
Oh,
Yep.
thank you. I think I had an earlier question. It's been really interesting. I just want to thank everybody. It's been a really nice educational Zoom meeting. I have a bunch of questions, but it really pertains to my own personal commercial use. As I mentioned to Andy, I've been using compost-based mixes for like 20 years. I've been fooling around with them for 20 years. It's not an exact science. It changes year to year. Watering, heat is definitely more important when using compost-based mixes than peat-based mixes. I've had more success with peat-based mixes, but I like using compost. I like adding the microbial activity, but it is trickier. Things go wrong often, and I do herbs, and herbs, can be very sensitive. Thyme does not like compost. Certain plants just does not like compost in its seedling stage. And I've never been able to find out why. It just is what it is. Same thing with basil. But other than that, it's an interesting product.
Well, one possible simple issue could be that the electrical conductivity is too high. And that might be a combination of the compost that you might be using might not be thoroughly finished or aged, or it could also be if you're using some organic amendments that are mineralizing very rapidly. And again, as I mentioned, it is really hard to get a handle on the rate of mineralization of nutrients in a mix that has compost in it inside of a cell, and a cell of any number of different sizes.
Oh, I agree. Absolutely. Yeah.
Thanks, Howard, for your comments. So I would like to wrap up this meeting today. Thank you so much for attending, everybody. Special thanks to Rosa and Andy for your great presentation. Again, just to inform you that today we don't have pesticide recertification credit. We have one more session after 2 weeks, in 2 weeks, which is scheduled for February. Oh no, what's the next one?
25th.
February
25th.
Yeah, February 25th, the same time.
2 weeks.
Hope to see, yeah, 2 weeks. Hope to see some of you there. So have a great rest of your day.
Thanks, Shuresh. Thanks everyone for coming.
Thanks.